Hello friends, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. And in our previous session, we had discussed about ample number of problems wherein we applied the concept of differential calculus to solve the real world problems. And apart from this, we learned how to find the function is increasing or a decreasing function. And this is in the same sequence, this is in continuum, the second session of the simple applications in differential calculus part 2, wherein we are going to discuss about how to determine the maxima and minima, which may be an absolute maxima minima or the local maxima or minima. So we are going to compute the extrema values for the functions. So the objectives of today's session are that after going through this session, you will be able to find the absolute maximum and absolute minimum of a continuous function on a closed interval AB. Apart from this, you will be able to find local maximum and local minimum of a function. So what do we mean by a maxima or a minima? Maxima means a value for which is higher than every other value in any interval. And the minima is any value of the function which is lower than any other value in that interval. So the formal definition says that let f be defined on an interval I containing a value c. Then fc, that is value of function at point c, will be value of function at point c will be absolute minimum of function f on interval I if fc is less than equal to fx for all values of x in I. Similarly, fc, that is value of function at point c, is the absolute maximum of function f in an interval I if fc is greater than fx for all values of x in that interval I. And these minimum and maximum values are actually the extreme values and hence known as extremas of the function in that intervals. So there might be a chance that the function is neither having minimum or not having a maximum in any interval. Likewise, there is a function fx is equal to x and fx is equal to x cube, which are not having any maximum or minimum in an open interval 0, 1. So, and apart from this function fx cube, fx is equal to x cube is neither having minimum or maximum value for any value in x belongs to R. So that means there are the function, it is not always possible. Say now we are having say some function, say this is the function. Now in some interval, say in this interval AB, this is the maximum value. And if say we extend the interval to be this, then this is the minimum value. But if we extend the interval to say again B, now this is not the maximum value because the next maximum value is this. So there is a concept of local minima and absolute minima and maxima and local minima and maxima. We are going to understand these concepts in this session. So in order to understand these sessions, this concept in session, we need to understand what is the extreme value theorem. The extreme value theorem states that if f is continuous function defined on a closed and bounded interval AB, then f has both a minimum and a maximum value on an interval AB. Now, in order to understand this definition, let's refer to this graph. In this graph, say we are given an interval AB. In the given interval AB, the value of function at point x naught, that is fx naught, is maximum in this interval AB. But if we consider the entire region, then this value fx naught is not the absolute maximum because we are having another point C whose value is greater than the value at point A. So it is to be noted that at x is equal to x naught, the point A on the graph is not the absolute maximum because fx2, at fx2, this value is fx2 and this fx2 is greater than fx naught. So that's why this is not an absolute maximum. But if we consider the interval AB, then we can say that the maximum value is at x is equal to x naught in the interval AB. So point A is the local maxima of the function. Similarly, f has the local minima at point B. Similarly, f has the local minima at point B, because graphically understand that what do we mean by the local minima or local maxima and absolute minima and absolute maxima. So, in order to formally define that what do we mean by local minima and local maxima, two definitions are given into your self-learning material, and what these definitions are that for local maxima is to be defined in a manner that suppose f is a function defined in an interval I. F is said to have a local or relative maxima at point C belonging to the interval I for each value of x belonging to I, for which C minus h is less than x is less than C plus h and x is not equal to C. We have fx less than C. So, for every value of x, every value of for function fx is less than the value of function at that value C, then this value C is nothing but the maxima, is nothing but the maximum or relatively maximum, because relatively maximum because we are taking an interval a b. Okay? So, we are taking an interval a b. Now, for the minimum part, suppose f is a function defined on an interval I, f is said to have local or relative minimum at point C belonging to I if there exists a positive number h such that for x belongs to I, we have C minus h less than x, C plus h, x is not equal to C, and we have the value fx greater than fc. That means at that point C, the value of the function is the minimum in comparison to all other values of function at any point x lying in the interval. So, this value C is nothing but the minimum value. So, I hope you understood what do we mean by the minimum and maximum part. But in order to calculate the minimum value and the maximum value, we are supposed to understand the concept of the critical numbers. Now, critical numbers are the numbers wherein the derivatives are 0, where then the derivatives are 0 or they are not defined. Because at the minimum value and the maximum value are to be the constants, and derivatives of the constant is always 0. ddx of constant is always 0. So, that means at the critical points the derivative should be 0. So, what are critical points? By the definition, if f is defined at point C, then C, that's point C, is the critical number of the function f if there are two conditions, if f dash C is equal to 0 or f dash is not defined at C. So, if f dash C is equal to 0, then this point C is nothing but a critical point and this number is known as critical number. So, there is a theorem which states that if f has a relative minimum or relative maximum at point C, then C is a critical number of f. What do we mean by this definition and theorem? We will understand by solving some of the numericals. Here is an example that wherein we are supposed to find the absolute maximum and minimum of the function fx is equal to x square in the interval -3 to 3. So, in order to find the critical number, we are firstly supposed to differentiate fx. So, fx is given to us as x square. So, first derivative of x, that is f dash x, will turn out to be 2x. Now, in order to find the critical value, we are supposed we know that f dash x is to be 0. So, this is to be placed at 0. Now, when this will be satisfied, this equation will be satisfied when x is equal to 0. So, when x is equal to 0, f dash x will be equal to 0 and f dash x is nothing but 2x. And x is equal to 0 is lying in the interval -3 to 3, which is given to us, that is -3 to 3. In this interval, we are supposed to find the absolute maximum and absolute minimum. Now, because x equal to 0 is lying in the interval, so let us find the value of maximum and minimum in this interval. So, in order to find the maximum and the minimum value. Let's evaluate the function at the extreme values and at the critical number also. So, extreme values are -3, critical number is 0, and other extreme value is 3. So, value of the function at -3 will be, because the function is f(x) is equal to x square. So, it will be -3 square. So, this will be 9. Value of function f(0) will be equal to 0 square, which is nothing but 0, and value of function at other extreme value 3 turning out to be 3 square, which is to be 9. So, the maximum value of the function is nothing but 9, and the minimum, absolute minimum, is nothing but 0. So, I hope you understood what is the role of critical number, how to find the critical number, and how to find the minimum and the maximum value, absolute minimum and absolute maximum value. So, there are some tests also going to understand the first derivative test and the second derivative test. To begin with, the first derivative test says that if the derivative f dash changes the sign from positive to negative, then the function f has a local maxima, and if the derivative changes the sign from negative to positive, then the function has local minima. So, from positive, so let me graphically show to you that the derivative, we know dy by dx, that is equal to dfx by dx, that is nothing but first derivative f dash x. So, variation of y with respect to x, so this is the positive part, and that means in this region, dy by dx is positive, and in this region dy by dx is negative. So, dy by dx is positive, dy by dx is negative. So, what is this? This is the peak value, this is the maximum value. And if we say again what the graph, so in this region, if we say in this part, the sign is, the slope is negative, and in this part the slope is positive. So, transformation is from negative to positive, and this is the minimum part. So, this is the minimum part and this is the maximum part. So, that means for local maxima, the derivative f dash x should be greater than 0 or should be greater than 0 to less than 0. That means the transformation should be from positive to negative, and if the sign of the derivative changes from negative to positive, it is the local minimum part. So, there is one more observation, that if f dash x is greater than 0 or if f dash x is less than 0 for every x in the interval I except at x equal to c, then f c is not a local extrema of f. We are going to understand these things in detail when we are going to solve the numericals. So, over here the first derivative test is consolidated into the few points. Let C be the critical number. That critical number is the point where the derivative is equal to 0. That means f dash c is equal to 0. Firstly, we are supposed to check if f dash c changes the sign from positive to negative. If it changes the sign from positive to negative at the critical point C, at the critical number C, then f c is the local maximum. If f dash x changes the sign from negative to positive at point C, then f c is the local minimum. So, in this case the slope is rising, so positive slope is there. Here it is decreasing, slope is negative. So, that means the derivative is changing the sign from positive to negative. So, that is why there is maximum. And in this case the slope is decreasing, here the slope is increasing, that means the derivative is changing the sign from negative to positive, and that is why there is minimum value. So, f dash does not change the sign at the critical point, that means at the critical point f dash c or f dash x is equal to 0 at point x is equal to c. So, this was the first requirement. So, let us apply the understanding to solve some numericals. The given example is that find the local relative extrema of the function. The function is f(x) is equal to 2x cube plus 3x square minus 12x plus 7. So, f(x) we need to find the derivative of this function. The derivative of this function will turn out to be 6x square plus 6x minus 12. So, the derivative turns out to be 6x square plus 6x minus 12. Taking 6 as a common value, you will get the expression plus x minus 2. Now, factorizing the quadratic equation, you will get 6 into x plus 2 into x minus 1. So, this is all about. So, that means there are 2 points, there are 2 critical numbers, there are 2 critical points for this function, and one is obtained by putting x plus 2 equal to 0, and other is obtained by putting x minus 1 equal to 0. That means x is equal to minus 2 and x is equal to 1 are the critical points, are 2 critical numbers, so of the function f. Now, we understand that how the polarity of the sign is changing. Since these two are the critical numbers minus 2 and 1, so substituting the values less than minus 2. So, substituting the value less than minus 2 in the first derivative, that is f dash x, which is nothing but this, that is 6x square plus 6x minus 12. By substituting the value minus 2, the value less than minus 2 is say minus 3. So, substituting the value in this, so you will get 6 into minus 3 square plus minus 3 minus 2. So, this turns out to be 6, 3 into 3 is 9 and minus 3 minus 2 is minus 5. So, this turns out to be 6 into 4, 6 4 the 24. That means f dash x for the values less than minus 2 is positive, f dash x is greater than 0. And for the value in the interval minus 2 to 1, say we put the value x is equal to 0. So, if we put the value x equal to 0 in this equation, so 6 into 0 plus 2 into 0 minus 1. So, this turns out to be negative because 6 into 2 is 12, 12 into minus 1 is minus 12. So, this turns out to be less than 0. So, the variation in sign of f dash x is from greater than 0 to less than 0, that is from positive to negative. That means from positive to negative, that means it is maximum. So, value of the maximum, local maximum rises at the point x is equal to minus 2. Similarly, if we calculate for the values x greater than 1, say we substitute the value 2, substituting the value 2, you will get 6 into 2 plus 2 into 2 minus 1. So, that means 2 into 2 is 4, 4 into 6 is 24, 24. So, this is positive. So, value for x is equal to 0 was less than 0, and for greater than 1 it is greater than 0. So, that means transformation is from negative to positive. From negative to positive, that is why the value, the local minimum lies at x is equal to 1. So, that means at x is equal to minus 2 we are having local maximum, and at x is equal to 1 we are having the local minimum. By substituting the value minus 2 and 1, we can find the values, that value of function f(x) at minus 2 turns out to be 27, and at value 1 it turns out to be 0. So, this is how we determine the local relative extrema of any function, wherein we are supposed to find the critical values, critical number, and thereafter we verify the variation in the change of sign from positive to negative or negative to positive. If the sign changes from positive to negative, it is local maxima, and if it is from negative to positive, it is minima. So, by solving this numerical, we learned how to determine the local or relative maxima and minima, and we learned how to apply the first derivative test. Now, this first derivative test has got some limitations, or rather in fact not to say limitations, it is somewhat a little difficult in comparison to second derivative test, and wherein we are supposed to check that whether the sign is changing from positive to negative or negative to positive, then only we can find that whether it is a maxima or minima. But in order to resolve this cumbersomeness or complicacy, the second derivative test came into the picture. What second derivative test says that it is actually useful when we are supposed to simplify the critical point by substituting f dash c equal to 0 and then just simply verifying what is the sign of the second derivative. And to be very specific, if the sign of the second derivative turns out to be greater than 0, then it is the minima, and if it turns out to be greater than less than 0, then it is the maximum value. What it is all about, we will be understanding when we are going to solve the numericals. But for meanwhile, we are supposed to understand that it is the first derivative test was very useful in finding the local minima and maximum of function, but it was a little bit cumbersome because we are supposed to find the variation in the sign around the point under the consideration, that is a critical point. So, in order to remove this complicacy, we introduce the concept of the second derivative test, wherein we are supposed to only calculate the sign of the second derivative of the function f at the point c, and what the variation of the sign recommends is given in these 2 points. The second derivative test says that let fx be a differentiable function on an interval I, and let c belongs to I. C is your critical point, critical function, and let f dash x be continuous at c. Then c is the local maximum if f dash c is equal to 0, that is the point to be the critical point, and if f dash c is less than f double dash c is less than 0. So, when the sign of double derivative is less than 0, then it is local maximum, and when the sign of double derivative is greater than 0, then it is the point of local minimum. But many a time there is a situation that f dash c is equal to 0 and f double dash c is also equal to 0. At that point of time, the second derivative test fails, and in that situation, we are supposed to use only the first derivative test to determine whether c is the point of local maximum or local minimum. So, this is an important observation, that if f dash c is equal to 0 and f double dash c both turns out to be 0, then the first derivative test comes into the picture. Now, there is a summarization of what is the second derivative test all about. You are firstly supposed to check that f dash c should be equal to 0. This is the first important condition. Secondly, you are supposed to determine the second derivative f double dash c, and if it turns out to be positive, it is a local minimum. If it turns out to be negative, it is the local maximum. If both turns out to be 0, that is f dash c is also 0 and f double dash c turns out to be 0, then the test fails. So, let's solve one more numerical. Now, over here the given function is x cube minus 3x square plus 2, and we are supposed to find the local or relative extrema, that is minima and maxima. So, fx given to us is 3 is x cube minus 3x square plus 2. So, f dash x should be equal to 3x square minus 6x. Taking 3x as common, it turns out to be x minus 2. So, the critical points will be that means the points at which f dash x is equal to 0. The f dash x will be equal to 0 when x is equal to 0 and x is equal to 2. So, x is equal to 0 and x is equal to 2 are the critical numbers. Now, we again determine the second derivative. So, second derivative will be f double dash x will be equal to 6x minus 6. So, that is 6 of x minus 1. So, 6x minus 6 is double derivative. So, at the point critical point 0 and x at critical point x is equal to 2, we are going to verify that how the sign changes. So, at x is equal to 0, the value of f double dash x, is will be equal to minus 6. By substituting x equal to 0, we will get 6 into 0 minus 6, which is turning out to be minus 6, which is less than 0. So, x equal to 0 turns out to be local maximum because f double dash x is less than 0. Substituting x equal to 2 in this equation, 6x minus 6. Substituting x equal to 2, what you are going to get? You are going to get 6 into 2 minus 6, that is 12 minus 6, that is equal to 6, which is greater than 0. So that means f dash double dash x is greater than 0 at x equal to 2. So x equal to 2 is nothing but local minimum. So I hope you understood how to apply the second derivative test, and you are advised again to solve more and more numericals so as to have better understanding. And these questions are frequently asked in your examination, in your assignments, and so you are supposed to practice more and more questions to have better understandings. Thank you very much.